Hello, everybody. My name is Seltzer Richman. Today, I am going to be talking about tracing Go programs with eBPF. My pronouns are he, him, and his. And I also want to point out that the slides that you're looking at right now, as well as the code that'll be live coding throughout this talk, are all available at my website, grant.pizza/talks/GopherCon 2020. So, diving right in here with a little bit about me, some fun facts. The stereotypes about millennials living in Brooklyn are pretty much true. I guess I have some weird hobbies. I enjoy brewing kombucha. I grow my own tempeh. I enjoy baking. I spend lots of time outdoors. I like to hike and camp, as well as my latest obsession has been foraging for edible mushrooms. I'm also a big Yankees fan, and this talk is pre-recorded, so if I'm a little bit grumpy in Discord, it's because the Yankees didn't just win the World Series. So here's why you should actually listen to me about Go and eBPF. So in college, I was very lucky to get a summer internship at Red Hat. I worked on a team developing container security tools. And in particular, my main focus was on a feature of the Linux kernel called seccomp. And most of my work was about increasing the usability and adoption of it. So I've talked a lot about seccomp in the past and written about it. Certainly, this talk is not about seccomp, but a fun fact about it is that it uses BPF under the hood. When I graduated college and moved on from Red Hat, I worked at a company called Capsule 8, where I helped develop a cloud security system. And there I was really immersed in the world of Linux. And as a security company, their product and research involves getting very fine-grained, event-driven information from the Linux kernel. And that is where I really dove into the world of using the tracing mechanisms with Linux. Now I work at a company called Oscar Health. We're a health insurance company where I work as a security engineer. I develop systems to protect our infrastructure, our networks, our workstations, our member data, all of the above. And through all this time, I guess about almost 6 years now, I've been writing production Go code. So I could genuinely say that I've been using Go for my whole career. I guess I've been using Linux for twice as long, but it wasn't until I started to develop tracing tools that we'll be talking about that I started to really understand the operating system, which is such a fundamental piece of software, at that fundamental level. Tracing has really enabled that. Keep mentioning tracing. Let's talk about what tracing is. So first up, to clear up, I'm not talking about distributed tracing, which a lot of you may be more familiar with. I'm talking about system tracing. And when I say that, I'm building I'm building a tracing tool, what I mean is I am building a tool to look under the hood at what particular processes are doing. This is by leveraging features of the operating system, typically, to inspect the activity of running programs. And by using tracing tools or developing tracing tools, we're looking to answer questions like, how much CPU time is a particular process using? What files is it touching? Is it starting other processes? And I tend to look at things from a security perspective, just the nature of my work and interests. So a lot of times I use tracing tools that I've developed to make sure that a program that I may not have access to the source code or want to bother looking at the source code, to inspect it when it's running to make sure I know what it's doing. Because, if let's say you're paying for a piece of software, you're going to want to know what it is, that it's doing what it's advertised to do and not, let's say, spying on you or something like that. So tracing tells all. An example of a tracing tool that you may be familiar with, may have used in the past, or potentially use very often, is strace. That ostrich, if you didn't know, is the mascot of strace. Found out pretty recently. So strace is a tool that will run a command or a program that you pass to it, and it will print out a line for every system call that is executed, or signals that are received, or changes to process state. It doesn't use eBPF, but I'm still going to demo it really quickly here. So here's what happens when you run strace on just an empty Go command. So starting with the system call for exec_ve for actually running the Go program. We have a ton of system calls. Definitely not going to go into to really any of them. We can see some signals being received. We can see executable memory being loaded in. We can see access to shared objects, all the way down to using the write system call to load our friendly Go help text, all the way down to an exit system call. So here's an example of a tool that actually does use BPF, and don't worry, we'll talk about what BPF is very shortly. But this is a tool called exec_snoop, and I could quickly demonstrate that as well. And what that will do is print out every time a program is executed. So you can see a lot. My shell does a lot, but I just ran Go, and you can see Go right there. The process ID, the parent process ID, things of that nature. So the reason that I'm showing you these two examples of tracing tools is to demonstrate the kind, I guess really, two very, just scratching the surface here, but to demonstrate the kind of questions that you may want to answer by using system tracing tools. strace or exec_snoop could be useful for figuring out security information, or for debugging, or finding performance issues. But as the title of this talk implies, we're going to be talking about eBPF. And plainly stated, eBPF is used to build tracing tools. eBPF is a virtual machine inside of the Linux kernel. And if that sounds very abstract to you, I think a very good analogy that's brought up a lot is comparing it to the JavaScript runtime that's inside of web browsers. So Brendan Gregg, a really fantastic engineer who works on eBPF tools, said that eBPF does to the Linux kernel what JavaScript does to HTML. And the reason that this is such a good comparison is because eBPF lets you write code. In the case of eBPF, it looks like C. I guess JavaScript is C-like, but you write that code and you attach it to hooks that trigger on particular events. And then the code, the eBPF code or the JavaScript code, run in safe sandboxes. Safe, but instead of running code in response to a button click like it would in, let's say, JavaScript, you can have your eBPF code run in response to, let's say, a system call, or network packets hitting a socket, or for particular programs being executed. There's a lot of hooks that you could attach eBPF programs to. Those are just a few examples, and we're going to be looking at another example for the sake of this talk, and it's Go related. I also want to say that you may have noticed a lot of hype about eBPF in recent years. It's definitely a very, very much talked about technology, and it's not going anywhere. And the reason, I want to share that the reason that I'm so excited about it, is that it's made learning about the Linux kernel so much more accessible. The operating system is a very large code base, and there's a lot of different pieces to it, and there's so much to learn. There's a lot of specialties within it. But writing small eBPF code has enabled me to learn that. And to possibly an even greater extent, it's enabled me to learn a lot about the Go runtime and how the Go runtime and compiler work by writing eBPF tracing programs. And we'll dive into that during this talk. So I want to just start with this extremely simple example of an eBPF program. This is a complete eBPF program. All this is doing is printing to a shared buffer between the kernel and between user space. So this is, again, like a very simple form. This is would be attached to some type of hook. Like I said, you could attach it to a system call. You could attach it to, let's say, like a network socket. I don't have much experience with that. Or you could attach it to, let's say, a symbol in a Go program. And we'll take a look at that in a second. But just very briefly, this function is log event triggering, which, that event that is created, it prints to a particular file, this helper function that we're not going to be using, but just a simple example. So the other feature of Linux that we're going to be using is something called a uprobe. I believe the U is user space. I guess that would make sense. Uprobes are one of the ways that you can have hooks which create events that eBPF programs run in response to. So compiler programs have something called symbols in them. They're just references to objects in our source code, like functions or variables. So, this screenshot that I have here in my slides is just printing out some of the symbols of a sample Go program that has, we can see here that we have some runtime functions. Go will put a lot of symbols in your binaries from the Go runtime. We can see here we have a symbol for main. It's in the main package, so it's main.main. It's always fully qualified like that, as well as this other function, in my program, main.function A. And we also just want to take a quick note of the fact that it has this memory offset associated with it on the left here. And the last thing that we're going to be using, or piece of technology that we'll be using, is something called BCC. And BCC stands for BPF Compiler Collection. It is many things, but you can think of it as a toolkit for developing tracing tools using eBPF. You can invoke it directly from Go, and lets you interact with running eBPF programs as well. So you can think of it as, using the compiler, using it as the compiler, as well as the bridge between an eBPF program running inside the kernel and your Go program that you'll be using BCC from. And, that's certainly abstract when I'm, just stating that. I think it's going to become a lot more clear once we start actually writing the code, which we'll do right now. And I just want to restate, if you missed it at the beginning, these slides contain all of the code, as well as, have the code on GitHub and links to that and everything. All the information that you need, if you'd like to follow along, is at my website, grant.pizza/talks/GopherCon 2020. So with that said, let's write some Go code. So we're going to start with a very simple program. And the point of this program is just to drive home the concept of what symbols and what uprobes are. So this is the simplest program that I can write beyond just having an empty main. But all it's doing is we have this main function, and it's calling function A, which does absolutely nothing. I'm also going to include one line here, and I don't want this to trip anybody up. Dave Cheney calls these pragmas. They're essentially instructions. They're these things where they're comments that start with go and then colon. And this no inline pragma is just to tell the Go runtime, or rather the compiler, to not optimize away this function A. And I'll show you exactly what I mean right now. So I'm going to build this program. As we expect, it does absolutely nothing. And I'm going to disassemble it. If you're not familiar with what disassembly is, when you take your source code and compile it, essentially a middle step between it being between it being source code and it being our compiled binary is assembly code. And disassembly is taking that binary and turning it back into assembly code. If you're not familiar with assembler, do not worry. So this is x86 assembly, and there's only 2 lines that I just want to point out. In particular, it's this line and this line. So starting off, we're in the main function, or in case of assembly, our main routine, and it's called by the name main.main. We're setting up the stack up here. You can ignore all these all the way down to here. We're using the call instruction here, and I've annotated it here. I wrote this disassembler to include, every time there's a call, it'll say what the name of the symbol is. So this call is passed a memory address. So in this case, it's it's in hexadecimal, so 0x45886B0 is the address. And if we look right there, we could see that exact address. So call is taking this memory address, finding that, and then would continue to execute the instructions that were underneath that until it would jump back to its calling point. So in this case, it does nothing, so that return would just jump right back to right after this call, which would continue on and exit the program. And the reason that I include that no inline comment line is just because Go is very smart and would recognize that this function does absolutely nothing and would just get rid of it. So that's why I included that. That's all it does. That was the, I just want to explain that because we're using something called uprobes. And uprobes will create an event whenever particular symbols are referenced. So if we were to attach a uprobe to main.function A within this binary that's at this particular path, it would create an event. And we can set it so that our eBPF program will be executed when that event is triggered. So let's actually write an eBPF program. So let's make this a little bit more useful, so so everybody is better able to see the actual use cases of this. So I'm going to just write a very simple web server. It's going to just respond with a little message saying I received a connection. I won't explain everything I'm doing, but all you have to know is this handler function will be called every time a connection is received. So let me just quickly run this out. And we'll listen and serve, or you have to pass this handler function, and we'll listen and serve. We'll do that. So all this is doing, it is just a simple web server it's hosting on port 8080, and it will just respond to any incoming connections with received connection from whatever the connection that it received it from. So let's actually build this so I can show you that. I'm sure you all trust me, and I appreciate that. So let's see. So I'm going to run it, and let's actually curl it. You can see received connection from localhost 8080. And you may also notice that there's no way, if let's say these are on different computers, we didn't put any logic in here for confirming that a connection was received. You can picture if this was a actual production web server where you're hosting an entire website, or some type of some web server that's serving documents or anything like that. You'd probably want to have logic in there. You'd probably want to have some type of filtering for who can hit your web server, or just logging. So bad practice on my part. So what we're going to do, and I'm not saying that this is necessarily the best way of adding that logic, we'll talk a little bit about that soon, is we're going to write an eBPF program that is going to attach to a uprobe attached to the handler function, so that we can trigger an eBPF program every time a connection is received at our web server. And we do that, again, by triggering every time our handler function is called. So let's just jump right in here. We are going to create a new Go program. You could picture them as being completely separate repos. I'm just creating them side by side for convenience sake. But what we're going to do is start by writing our eBPF program. Like I said, eBPF essentially looks and feels like C. So I can have this in its own file for convenience sake. I'm just going to put it, since it's a small program, I'm just going to put it in a string here in our Go program, which we'll use ECC. So I'm going to start with an include statement. I'm going to include ptrace. And the first thing I'm going to do is I want to set up something called a perf buffer. A perf buffer is a way of enabling communication between the eBPF program and the user space Go program that's using it. And we'll see a little bit more of that very soon. But for now, the way you set it up is using this macro BPF perf output. And we're going to name this perf buffer events. Now in the actual meat of our BPF program, I'm going to call this function was called, or even handler was called. It takes one parameter. We'll see what we can use that for very soon, but I'm not going to dwell on it right now. And let's just, simplest log possible. Let's just have a message, handler function was called. And we're going to send this up to our Go program that is actually installing this eBPF program for the Go program to do whatever it wants. In our case, we're just going to print it out. So we're going to take that perf buffer, and we're going to call perf submit, which you can guess what that does. It takes this context object, or struct. It's going to take a reference to our message, as well as it needs the size of the message. Don't forget the semicolon. Sorry, Go programmers, we need semicolons in BPF. So that is our BPF program. Now what we're going to do is we're going to write a Go program that is going to compile that, load it into the kernel, associate it with our user space handler function in our other Go program, and it's going to listen for output from it. So let's break it down. First off, BCC, this library that I told you about, has a concept of modules, and I don't want this to throw you off. It is not at all like kernel modules. eBPF does not create kernel modules. That's a separate concept. So let's not worry about that argument for now, but we're going to create a new module here, which will take this string of the eBPF program. If you had it in a separate file, you would just read the file and pass it in as a string anyway. I created this module. I'm going to use it to create a uprobe. So eBPF module.load uprobe, and I'm going to associate it with this handler was called function in our eBPF program. This will return a file descriptor as well as an error. So let's make sure that we check that error. We'll just log.fatal for now. And then we're going to use that file descriptor to attach it to the function in Go, this handler function. So the way we do that is we're going to do eBPF module.attach uprobe, and we have to pass two important things, or really three important things. So first off, we have to pass a binary that this symbol can be found in. So we'll pass that at the command line. Let's also pass the name of the symbol. In this case, it's main.handler function. Remember that functions have to be fully qualified with the package. And we're going to pass in this file descriptor for our uprobe that we created right here. We can also pass an argument here for the process ID. So if we want to trace just a very specific process, we could pass it there. If you pass -1 to this particular function, it will just trace all processes. Fatal that error. So the next little bit of code, I don't want to dwell on too much. This is how we set up the perf buffer on the Go side. So first off, we create a table. We pass in the table ID, which is just events, as we called it in BPF, and we pass in the actual module. We then create a channel. Let's just call it channel for now, or how about let's call it perf channel, which is just a channel of bytes. And the cool thing here is that's what we're actually going to be reading the output off of. So we can use a facility of Go that we're familiar with for interacting with the Linux kernel, which is, I think, a really cool part of or design of the BCC bindings for Go. Next, we have to actually start that. Let's see, what am I doing here? Oh, we actually have to initialize it. So. So let's see, bcc.init map. We're going to pass the table, and we're going to pass the channel, and let's not worry about this argument for now. Okay, now we start the channel. We'll defer closing it or stopping it. And now we're going to start a Go routine that will read off of this channel for. So we'll have an infinite loop. This will run until we hit Control-C. I'll set that up. So we're just listening for these raw bytes, which again are set up to read from every time our eBPF program does events.perf submit, and we'll just print it out. Let's print it as a string. And like I said, let's just listen for Control-C and block on that. What is it? Signal.go. Just interrupt. Okay, so I know that's a little bit of a program. So just to quickly review, we have our eBPF program, which is just submitting this log message. That's it. We're submitting it through a perf buffer called events. Next, we are going to install that in Go code using BCC. We're going to attach a uprobe to the function that we want to trace. In this case is the handler function in this other Go program, two separate programs. We set up the output from it. We're reading it from a channel in a separate Go routine, just printing it out when we hear it. And then we're listening for Control-C. So let's actually run this. First off, let's rebuild our server. Oh, I'm messing it up. Sorry. Our web server. Oh, I already have it running somewhere. Where do I have it running? Oh, in here. Let's get rid of that. All right, so we're going to start running that. And let's also build our tracer. Okay, so we do need special privileges for installing eBPF code. So I'm going to have to do sudo. And I have to pass the actual binary. So at this point, what we have is we have the web server running in this tab here, and we have our eBPF code attached to this symbol here, handler function. So now every time that handler function is executed in any instance of this demo web server, not just this particular one, but we'll just have one for now, it will execute our BPF code, which will send up our message to our Go code in this tracer, which will just print out our message. So curl localhost 8080, we did receive a connection, so we know that our handler function was called, and we could confirm that with our impromptu logging infrastructure that we wrote with eBPF. So we can see handler function was called. That was trigger our uprobe with our eBPF code attached to it, and there you go. Woo! So here's why this is useful. So logging and debugging of programs that are already compiled, deployed, or running is a pretty cool thing. So let's say, let's say you don't control the source code, or you've already started running it and you don't want to, to recompile it or something like that to do some investigation. So you might want to do something a lot more intricate than just printing out a log, and we'll take a look at that right now for an already running program. So eBPF is a lot more powerful than just logging. You can quote me on that. So something that I want to show you is that eBPF programs have access to the actual virtual registers of the programs they're tracing. So as programs are running, they're populating the CPU registers, and when the function that it's attached to is about to execute, you can get the state of what those registers are. And that includes a reference to the stack, and that is in this particular register here, SP, stack pointer. And you can actually see that in code that this definition here depends on architecture and version of your kernel, certainly, but that is what this context object is, or context struct, I should say. So what we're going to do next that I want to demonstrate is tracing Go function arguments, actually getting the arguments that are passed into functions. So when switching context between different functions, the Go runtime places the arguments at offsets from the top of the stack based on their size and order in the list of arguments. So other programming languages like C typically put them in registers. So let's say you call a new function, you're passing in 2 arguments. C will put those arguments in certain registers, and then the assembly code of that function will reference those registers. Go does not do that. It puts them on the stack so that when you enter into your new stack frame, the Go runtime is programmed in such a way to pull the arguments off of that. Let's actually program it. So we're going to go back to a very simple program. Let's just call it function. I'm just going to call this function B. And let's pass in a couple of arguments. Let's say x, which is an integer, and y, which is an int 8. 2 different data types because we don't have generics. So we're going to keep this no inline pragma. Again, it's just so that Go doesn't optimize it out. Go is a lot smarter than, or actually, I'm sure everybody knows that it's pretty smart. So actually, instead of function B, let's call this add 2 numbers. And we'll print out that plus that equals that. So we'll do x, y, and x plus y. And we'll do add 2 numbers. Let's add 42 and 3. So this should print 42 plus 3 equals 45. Okay, so let's kill that web server, kill that, and let's rebuild our demo. And we can see when we run it, 42 plus 3 equals 5. Exciting stuff. So now we're going to adapt our eBPF code to get the arguments. So in order to do so, we're going to need to do a little bit of arithmetic. So we access the top of the stack using the SP field of the context struct that were passed, and we're gonna look at all of this in code. Don't worry. We're going to calculate the arguments offset off the stack. So if SP is pointing to the top, we're going to have to go a certain amount of bytes down from that to find the where the arguments are. We're going to read the arguments off the stack using a helper function called BPF probe read. We're going to send them via a perf buffer in the same way we did for our last program, and then we're going to parse them in Go using the encoding/binary package, and I'll certainly show you that. Don't worry. So when it comes to calculating stack offsets, it's pretty basic arithmetic. So first off, arguments start 8 bytes off of the stack. The first 8 are for something called a base pointer, and that's how let's not even go into it. So parameters are padded on the stack based on the largest data type among them. So the limit is 8. So on the right here, we have the size in bytes of all the different, or not all of the different, but most of the different data types in Go. And I like to call this concept the window. So the window size is based on the largest data type. So for example, if you have 3 data types and one is 1 byte, one is 2 bytes, and one is 8 bytes, that window size would be 8 bytes. So the parameters are put onto the stack in order and are put at certain locations based on whether or not they fit into the current window. And if they don't, the stack is padded until the start of the next one, and then that parameter is added. So in concept, the parameter ordering affects the memory efficiency. So if you have 1 byte, if the window size is 8 and you put on, let's take a look at an example. before we go into that. So let's look at, in the case of our example of the code that we just wrote, the int data type is a default based on the size of or the architecture of your computer. Typically, on x86 64 Intel processor that most people use. I believe the same for ARM. Actually, I can't confirm that, but I'm pretty sure int would be 8 bytes. Int 8, that refers to the amount of bits, that 8 bits, so that's 1 byte. The first parameter starts at stack pointer plus 8, and it takes up 8 bytes. The second parameter would start at, right after stack pointer plus 15, so that's SP plus 8 through SP 15 for the first parameter. So we can just read the byte at SP plus 16, takes up 1 byte, and then there would be 7 bytes of padding that we can ignore. So now we know where to actually read them from. Let's actually write the eBPF code. So this can go away, and let's start by getting that reference to the stack. We'll call it stack address, and we'll just do context and reference SP. For the first argument, since it's 8 bytes, we're going to use long. I have a table that we can reference for the data types in eBPF code compared to Go code. But for now, for the case of simplicity, just believe me that a long will be 8 bytes. So it'll correspond to the 8 bytes that are used in the integer in Go. So we're going to use this helper function called BPF probe read, and we're going to use that to read in to argument 1. It takes the size of that argument and the starting address, which is stack address plus 8. Now we're going to just submit that to the perf buffer in the same way we did before. Take a reference to that argument and the size of it. And next, we'll get the second argument. A char in eBPF code is 1 byte. And let's just copy this. So I'm running out of time. So that's argument 2, and we'll submit it. Let's rename handler was called to add to numbers was called. Add to numbers is the symbol we're attaching the uprobe to. And now we have to change this. So I did mention that we have to encode the bytes that come out of the eBPF code. So first off, we're going to read from this perf channel, and that will give us the raw bytes of the argument's data. So we have to encode it. So I'm running on a little endian machine. That's something that you can easily look up for the type of processor you have. Likely, if you have an Intel processor, it'll be little endian. And we're going to essentially cast those bytes that we received as a uint64 on a little endian architecture. So we'll do the same thing for the second argument. And it doesn't matter if you do 16 bytes since it's very small. Or 16 bits. We don't have an option for a single one. And we'll just print out first and second, or let's make it a little prettier than that. Okay, so just to quickly review, we've changed our eBPF program to actually read some arguments off of the stack, which we calculated beforehand. I just caught that, I did that. To read them and then submit them with a perf buffer. And we are attaching the uprobe to our user space Go function here, the symbol in the compiled binary. We're going to read them off of the perf buffer in the same way as before, and we're casting them or making sure that we treat them as little endian data. So let's build that. The tracer and no, what is this? Okay. Okay, so first off, I'm going to run the tracer. Enter in my password, please don't look. And now, when I run our demo code, it's doing what it's advertised to do. 42 plus 3 equals 45. It's adding two numbers together. And we could see that our eBPF code caught that, and it's just logging it for now. Woo! So again, this may seem like a roundabout way, like why are we doing this? So eBPF code runs with access to all of memory. So if you have a very complicated Go program that as certain functions are called that change an internal state, and you want to verify certain parts of memory, eBPF could be used to do that. So instead of getting a certain offset off the stack, you can enter in memory addresses for different places in RAM. You can access data in other processes from your eBPF program. It has a lot of access and a lot of power. One more thing that I actually want to show you is it also has access to write to memory. So instead of actually printing out these arguments, we're actually not going to submit anything back up to user space. We're going to do something, I guess, a little malicious, and we don't want anyone to know about it. We're going to get rid of this. Instead of reading, like I said, we're going to write. So let's say we want to change the argument before it's passed into, or right as it's passed into our function. We can use a helper function called BPF probe. Instead of read, we're going to do write user and pass in the offset off of the stack where that argument is stored. We're going to pass in the data buffer, which is just this long, and we also need to pass in the size. And don't forget your semicolon. So in this case, we're just actually writing to the stack, which is just a location in RAM as our other program is called. So let's close our old tracer. We haven't made any changes to our demo program, so executing it, there is nothing unpredictable about it. It takes two numbers that we've hard-coded, 42 and 3 equals 45, and we could even, like I believe I showed you earlier, actually look at the disassembly of this and see where that 42 and 3 are passed in. I said 5 before, I meant 3. 42 plus 3 equals 45. I know math. So that's hard-coded, but once it's running, it is susceptible to our attack. So I think I need to rebuild it. I just love semicolons so much. I put one there. So now we're running it. And now if I were to have it running, so this is going to intercept when we run our demo, we can see that it has changed that first argument before the function starts getting called, So it's actually going to do the math on the new argument and make it, actually change it. So if I were to stop running that, it will go back to the way it was before. Potentially could be used for nefarious purposes, but also, that certainly has use cases in fault injection. So if you want to, let's say, if you're relying on an interface as part of the operating system or even the hardware or another program, and you want to create fault injection to make sure that your program is handling all possible errors, you may use that to write over data. I guess you could use it for. I could think of a lot of security purposes and research that you might want to use that for from a security perspective, as well as for example, like possibly even writing a fuzzer that way would be interesting. Don't know if it's the best way. Whatever. Regardless, it's really fun and cool in my opinion. So I just want to close with a couple of things. So first off, I have a project on my GitHub if this has really interested you, where I'm trying to generalize this tracing of Go programs. I'm seeking to have the functionality and use of strace in the same way that you could just invoke another program and it prints out all of these system calls. I'm trying to write a tool that will do that except for a Go program and print out the symbols in the Go program. Check that out. If you make a contribution, maybe I'll send you one of these cool stickers. That's on my GitHub. There are so many different possibilities of what you could do with eBPF, and I barely even scratched the surface of what we can do, either for tracing Go programs with eBPF from Go, or even just using Go as a catalyst for writing eBPF code. A great place to look for how you can learn more and projects that you can get involved with is eBPF.io. It's a new website that some really cool people in the space have started. Even like BCC is a toolkit and has a lot more tools beyond just exec snoop that I enjoy playing around with. Thank you so much. Enjoy the rest of GopherCon. Cheers.